Hello everyone, I am Rati Ludhani. I am pursuing PhD at Department of Mathematics, IIT Bombay. Today we are going to discuss week 5 assignment. These are sample questions related to lecture 10 and 11. Okay, so let's start. Consider the ring Zi, which is a plus ib, a comma b belongs to z, where I is equal to root minus 1. Which one of the following is a reducible element? Okay, so what is a reducible element? Do you know? Okay, so I'll just discuss what. Okay, I'll just write first a reducible element because it is easy to see then what are reducible elements. Okay, so C is said to be a reducible element, irreducible element if C is equal to I'd say if there exists or I'll write that is better if for any no okay non unit element. Okay, these are non-unit elements. A non-unit element C is said to be a irreducible element if for any C1 and C2 in R, ring is R, okay, a irreducible element of ring R. If for any C1 and C2 belongs to R, C is equal to C1 into C2, then either C1 or C2 is non-identity. Is identity. Again I'm saying identity. This is not identity, unit is a unit element. So basically if you write C is equal to C, if there exists some C1 and C2 in R such that C is equal to C1 into C2, then one of them has to be a unit element. Okay, so you cannot actually write in a form of product of two non-unit elements. Any non-unit element, if you are able to write it in the product of non-unit elements, then it is actually reducible. So the negation of this statement is what? So that is a reducible element. So why I said first irreducible, because that is more of a standard definition. So what are irreducible elements? So a non-unit element. So we only discuss about non-unit elements. So a non-unit element is said to be a reducible element of ring R, if you are assuming that is the case. Said to be a reducible element of a R if there exists, or again I'll write there is an element C. So if there exists C1 and C2 belongs to R, or okay, non-unit, there exist non-unit elements C1 C2 belongs to R such that C is equal to C1 into C2. So you have two non-unit elements and this is the case. Okay, is that okay? The definition is clear. If you can write it, if you can write it as the product of two non-unit elements, then it is an irreducible element. Okay, so and it should be a non-unit element at first to begin with. So let's see, what do you have in your question? I'll just make it a scrolling vertical. Yeah. So right. So what does this say? Consider the ring Zi. You have the ring Zi. So this is ring of integers only, like a plus ib Gaussian integers. A comma b belongs to Z, where I is your iota. Which one of the following is a reducible element? So basically, if you can write it like this, where these are non-unit elements, then you are done. So can you tell me what can you do with 4? Like, can you write it as the product of two non-unit elements? Yeah. Can you write 4 as the product of two non-unit elements?
2 into 2.
Yeah, exactly. Very good. So 4 is equal to 2 into 2, and these are non-unit. Why? Because there is no inverse which you can have, like for 2. So 2 into something, if there exists or not. So for example, there is some element a plus ib, and what is the identity here? That is 1, because we are in integers. Z is a subset of it. So 2 into a plus ib is equal to 1. So you have 2a plus 2ib is equal to 1. Now this is your 2a is equal to 1 because a and b are integers here, right? And so this is your complex part with iota, and 2a is your real part. Real means we are in integer, so that is the case. So 2a should be equal to 1 if you compare it up, and here 2b. So basically you are writing 2a, 2b, and you have iota, and this is 1. So you can write it like 1 into, so iota into 0. So that is exactly 2a is equal to 1 and 2b is equal to 0. So this implies b has to be 0 because you are in integers. So b is an integer, and 2 is like, if you have so you cannot have like 2 into something is equal to 0. And here what will you get? A is equal to 1 by 2. But does 1 by 2 belongs to this set? No, because this does not belong, right? Because we are in integers. So zi is integer. So 1 by 2 does not belong here. So this implies 2 is a non-unit element. So this works. So you can write it 4 is equal to 2 into 2. So 4 is an reducible element, and not n is a reducible element. Okay, let's see B. 2.
1 plus I into 1 minus.
Exactly. So 2 is equal to 1 plus iota and 1 minus iota. So if you don't know this, you can always try it out. Like maybe it is not coming into your mind, like if you can write, because 2 is still a small number. If you have some bigger number and if you want to see this, then you might stuck in that case. So you can always try like this: a plus ib. This is exactly this, you're sure. So what is this? 1 plus iota square minus, so this is 2, right? So this is exactly 2, this is 2. But if you want to find out, if you cannot figure out by just seeing it, you can always try with this. So if 2 can be written, so whenever you want to check something reducible or irreducible, just take some random like arbitrary 2 numbers, like of this kind, because these 2 belongs to zi. And now you just try out if you can find a b c d as per your ring. So a b c d here belongs to z. So if you can find this, then you are done. So you start with like this, and I'll add a page again. Yes. So you have 2, and here if you multiply, what will you get? I'm writing directly. Just multiply and club the iota part and the real part. So this is AD plus BC. So you have AC. So if you compare, so this is your Z part, integer part, and this is iota. So here you have kind of iota into 0. So if you compare, this should be equal to 2 and AD plus BC should be equal to 0. Now try to find if you can have something like that. So you want here to be 2. So can you find AC minus BD something like that or not? Okay, let's see. So as you can see, if you take for example, let's see, so you have A and C is equal to 1. So I'm just trying to have 2 here first. So A and C is equal to 1, and take you want to have it to be 1, right? Minus 1. So what will you take? You just take B, either B to be minus 1 or D to be minus 1. So let's take B is minus 1 and D is equal to 1. So let's check if this satisfies the second equality or not. So A is your 1, D is your 1, plus B is your minus 1, and C is your 1. So this is exactly 1 minus 1, this is 0. So yes, there exists some A, B, C and D in integers such that you have this scene. So this implies 2 is equal to, so basically if you take D equals to minus 1, you will get, it's just like writing in a form. So both phase is fine, like 1 plus iota into 1 minus iota, 1 minus iota into 1 plus iota, because you are in a commutative ring. Right? Is that clear?
Yes.
Okay. So B is okay. Now, okay, so 2 is irreducible, and now what about 5? So 2
2 plus I into 2 minus.
Exactly.
Or
That,
1 plus 2I into 1 minus 2.
yeah. So as you said, exactly, if you take 1 minus 2 iota into 1 plus 2 iota, you will get 1 plus 2 is 2 square. Like if you multiply, I square will make it plus, and this is A square minus B square. So this is 5. Or you take this, you will get 4 minus and then again I square, which make it plus. So 1, this is 5. So same thing is happening. Now 5, you can write it as a product of two non-unit elements. So again, you can always check non-unit if these are non-unit elements or not. Actually, if you go with the process, you will always find out that this element should be your the inverse of this, and check if this is an element inside your sorry, what should I say, like if this element belongs to your ring or not. So for that, sorry, so you must have rationalized in 12th or like these kind of things. So this you will get this, and 1 minus, sorry, plus 5, sorry, 4, 1 minus 2 iota by 5. So as you can see, you have 1 minus 1 by 5 minus 2 by 5 iota. So these should be integers according to your ring, but these are like rational numbers which are not integers. So you cannot have the inverse in this ring. So these are really non-unit elements. So unit element is like which is invertible in your ring, like there is some inverse for it. If that is not, then these are called non-unit elements, right? So you can check for everything, even with 1 minus iota. If you take 1 plus iota and 1 plus 1, that is again 1 by 2 plus 1 by 2 iota. So again we need 1 by 2 in your ring, but that is not the case. Okay, so similarly, if you want to try with this process, because if you cannot see 5 is really inside this ring or not, so you just try again with your base process, which always helps. If you can find ABCD, then you are done. If not, then this is irreducible. And if you want to prove that this is irreducible, you have to go with this process, because you have to show that there does not exist some such abcd such that you can write it like in this form. So try with this, you will get either this or this. Is that okay? So 5 is also reducible. Is that okay? Any questions on this? Okay. Okay, great. So all of the above. So question was asking which one of the following is a reducible element. So all are these reducible elements. Okay, let's move to the next question then. Which one of the following is a prime ideal of Z? Okay, let's see. Okay, what are prime ideals? Okay, so
If A
what?
comma B belongs to ring,
Yeah,
then AB belongs to ideal. If A belongs to ideal, or B belongs to
exactly. So a ideal is said to be prime. Exactly, very good. Is said to be a prime ideal if AB belongs to I, then either A belongs to I, sorry, an ideal I, okay, is said to be a prime ideal of the ring R if AB belongs to I, then either A belongs to I or B belongs to I. And I should start with AB belongs to the ring R. Okay, that is be a prime ideal of ring R if for AB belongs to R, AB belongs to I, then either A belongs to I or B belongs to I. One of them has to be inside your ideal. So that is a prime ideal. I think I should say proper ideal. This should be proper ideal. Okay, it should not be the whole ring. Okay, this should not be the whole ring. So a proper ideal I is said to be a prime ideal of ring R if for AB belongs to R, AB belongs to I, then either A belongs to I or B belongs to I. Why I said this should be belongs to I, because we have just unknown some A and B, so we should start with where AB belong. Okay, so let's try what is happening here. Okay, so you are in the ring Z, which is definitely with the addition and multiplication, or normal addition and multiplication. Then can you write 4? So you need to check. So 4 is actually here. What does that mean? This is actually this ideal generated by 4. So this is ideal generated by 4. That means 4 into something, let's say this is A, such that A belongs to Z. So this ideal contains all the multiples of 4. Obviously 0 is there, because if you take 4 into 0, you will get 0. So you have all the multiples of 4 in your ideal. Similarly in this, similarly in this, similarly in this. Okay, so let's try what is happening. So everything means this. Okay, so let's take so for 4, the ideal this. Can you give me an example of such kind, like if this is happening here or not? Yeah,
2 into 2. But
yeah,
2 doesn't belong to ideal of 4.
exactly, very good. So if you take 4 belongs to I, so if you write 2 into 2, which is equal to 4 belongs to I, this is your like A. Okay, I should use another representative here. So it's like, let's say R. Okay, R is fine. So you have R belongs to Z, exactly. So if you take A and B this, then 4 belongs to I because all the multiples of 4 are here, but 2 does not belong to I, and these are for both case, like 2 does not belong to I. So A and B does not belong to I, but AB belongs to I. So that is a problem. Implies this is not a prime ideal. Why 2 does not belong to I? Because here you only have the multiples of 2, and you don't have something like 1 by 2. So R is not like 1 by 2. So this is not the case because you have only integers to put here. Right? So this is not a prime ideal. Exactly. Similarly, if you try to do with 5, 6 and 9, so you need to check 5, 6 and 9. So B, I'll keep it for last. Let's take C first. C is your 6. Here what can you take? 3 into 2? Yeah, sorry. 3 into 2 is equal to 6, which belongs to I. But 3 does not belong to I and 2 does not belong to I. That is clear because this is what? This is your set multiples of 6. So this is your set. So 3 into 2, which is 6, belongs to I, but 3 does not belong to I and 2 does not belong to I. So this is a problem. So this is also is not a prime ideal. Exactly. Let's see D, which is 9. Yeah. What can I take for 9?
3 into 3.
Exactly. So 3 into 3 is 9, which belongs to I, but 3 does not belong to I. So A into B belongs to I, but 3 does not belong to I, and which gives a problem. So this is not a prime ideal either. So as you can see, you can find the multiples only if you are in the case of non-prime elements. So non-prime means I'm not considering one. So I'm just saying if you have prime number, then you can always think of this, like you cannot take the, so for example in your case B, which is your 5. So this is 5R, R belongs to Z. So here you can see, like you cannot take something like 1 into 5. That is the only possibility here because this is a prime number. So so we need to prove that this is a prime ideal. It looks like this because we are not able to find A and B, because if you take A and B, you are anyway having some multiple of 5. Okay, so let's see if we can. So okay, so let AB, so AB you have AB belongs to 5. Then what will happen? Then AB should be a multiple of 5. Let's say this is 5R1 if you want to write, let's say 5R1. So it should be a where R1 belongs to Z, where R1 is some element in some integer. Then now if you want to write, if you want to check either, so what should happen? So if you want to see, so 5 divides AB, this implies 5 divides AB. So this is the definition of prime. If 5 divides A, if 5 divides AB, then 5 divides A or 5 divides B. This is the definition of prime, right? So what should happen? One of them should be a multiple of 5. Actually, I would say let's do it other way around. So let's take the contra positive statement. So what can you try? So what is the contra positive statement of this? You can always do the earlier way. That is not a problem. Contra positive statement is take A does not belong to I and B does not belong to I. So this is N. This implies AB does not belong to I, right? what will be the contrapositive statement? This should not belong to I, so or will become and. Both these elements, so negation of this part should imply negation of this part. So this is A and B. A does not belong to I and B does not belong to I. This implies AB does not belong to I. If you can prove this, then you are done, right? So I think this is better. So take A. So let A does not belong to I and B does not belong to I. What does this mean? So I is your, definitely, which is your ideal, this 5, right? This implies A is not a multiple of 5 and, so this is both. B is not a multiple of 5. Both are not multiple of 5, right? So what will happen? If you take AB, then AB is not a multiple of 5, right? Which is convincing, I guess. So AB,
Yes.
right? So AB is not a multiple of 5 because there is no factor in A and B, both in that there is no factor of 5, because there is nothing like which if you combine you will get 5, like 2 into 3 is 6, so you get 6. So with 5 this is not the case, which is the definition of prime, actually prime number in Z. So this implies AB does not belong to this, and which gives your result. So this is a prime ideal, right? Any doubt? So this,
No.
okay, great. Feel free to ask. If you want to write in chat box, that is also fine for me. Okay. Read the following statements and choose the correct option regarding these statements. Okay, so what is your statement here? S1 is, if A and B are ideals of a ring R, okay, we have not assumed, so let's say ring R, it's easy to assume, then AB is a subset of A intersection B. So this is your first question. And second is, okay, so let's try first. Okay, so if A and B are integers of a ring R, then AB is a subset of A intersection B. So can you give me a definition of AB first? What is AB? So these are two ideals. What is the product of two ideals? Okay, I'll just write. So this is what? This is the smallest ideal. Smallest ideal such which contains, sorry, smallest ideal which contains not this, yeah, which contains the set AB such that A belongs to A and B belongs to B. So the ideal which contains the product of product of elements of A and B. Okay, so the smallest ideal, that is your AB. Okay, and okay, so you can check the lecture, I guess, if I'm not wrong it is 9 or maybe 10, I'm not sure. So you can check for the definition, why this has become the definition, why this is not enough and everything. So this is the definition for now. Now you have so you need to check if this is AB is contained in A intersection B or not. So you know the thing that, okay, what is A intersection B? Is that an ideal first? So what is A intersection B? So as always, A intersection B is the set, is the elements of A and B which are in both A and B, right? Is that okay?
Yes, ma'am.
Okay, now I'm saying like A into B, A belongs to A and B belongs to B, is contained in A intersection B. Is that okay? So this is your question. So, uh, so I'm saying this is your case. AB, where A belongs to A and B belongs to B, is contained in A intersection B. So if you want to prove that, what should we prove? That all of these elements are in A and also in B. So let's check. Take an element AB such that or maybe where A belongs to A and B belongs to B. Then if you see, A belongs to A, right? A belongs to A. So in the definition of ideal, what we have in the ideal definition? So let's say ideal is I when if it satisfies two properties, that A1 plus A2 belongs to I for all A1, A2 belongs to I. So if you have any two elements, then some should be in your ideal. Second thing, A into R should belong to I for all A belongs to I and R belongs to R, the ring R. Okay, any ideal of a ring R is what? If it satisfies two properties. Actually, there is one more property, not one more property. We should start with non-empty set. Non-empty set I, or I should say, okay, I'll just write it properly. Non-empty subset I of the ring R is said to be an ideal if this is true and this is true. So two things should be true to happen, like to say that this is an ideal. So if you see, so this is just for the reminder, what is the definition of an ideal. So because of that, if you see A into B, so you have A into B and you are in commutative ring, so R into A into R doesn't matter, these are the same elements. Okay, so here if you see, A belongs to A, so B belongs to B, which is a subset of R, because ideals are subset of R. So you have some element of A and it has been multiplied with an element of the ring. So according to this second property, AB belongs to A, right? Also, if you see, this is also a subset of R, and ignore this for now. So B belongs to your ideal B, and this element A is an element of a ring. So according to this second property, AB should also belong to B. Is that okay? Is that okay? Okay. So AB belongs to A intersection B. So this element belongs to both of the rings. So AB belongs to A intersection B. And you have considered any general element of this set. So what this implies? So this implies the set AB, I can change color, AB, where A belongs to A and B belongs to B, is a subset of A intersection B, right? So you have this. Now according to the definition of AB, and this is your ideal, okay, you can check A intersection B is an ideal. So what you need to satisfy, so let's check quickly. So A intersection B is non-empty because 0 is there in both of these ideals, because ideal should be non-empty, right? So actually non-empty means 0 belongs to I, so it turns out to be, don't worry. So why I'm saying that, if you said non-empty, that means there exists some element here, and just take R to be 0, then 0 into that element, which is 0 should be I, should be in I, so 0 is always there, right? So A belongs to B, in A intersection B, 0 belongs to I, so this is non-empty. Second thing, if you take the sum, so if you take A1 plus A2, this is in A intersection B, this is in A intersection B. So firstly A plus B, so this is in A, this is in A, so A plus B should be A1 plus A2 should be in A because of this property, because A is itself an ideal. Similarly for B, A1 belongs to B and A2 belongs to B, so the sum should be in the ideal B because this itself is an ideal again. So this element belongs to A intersection B, right? Similarly, if you take A into R, so A is okay, A looks like an element of A. Okay, just take A to B. A is an element of A intersection B, and you have R. R is some element of ring. Then A into R should be in A intersection B, which is clear because A belongs to A. So A into R should be in A, right? A belongs to B, so B into R should be in B. So this is in the intersection. So this itself is an ideal. Okay. Now from the definition says smallest ideal which contains the set this. So this set is contained in A intersection B. So definitely the ideal which we are looking for A into B, it must be contained in A intersection B because that is the smallest ideal. So this implies AB, the smallest ideal which we are looking for, it must be contained in A intersection B. Is that clear? It cannot go
Yes.
it cannot go beyond A intersection B because A intersection B is itself an ideal. It could be smaller than that, or it could be equal to A intersection B. It can never go beyond that. So that is your thing. Very good. So this S1 is true. So this one is correct. What is the second statement? If A is an ideal of a ring R and 0 belongs to A, then A equals to B. Sorry, A equals to R. So this is saying S2 is, what is that? Okay. If A is an ideal, then and 0 belongs to A, then ideal of a ring R, of a ring R and 0 belongs to A, then A is either, what is that? Then A equals to R, not even any condition, A equals to R. So it is saying A is an ideal and 0 belongs to A, then A is equal to R. But as I said just before this, 0 is always there because this is non-empty. So there must exist some element, let's say whatever be that element. Then from this condition, if you take R to be 0, then whatever you have element, then A into 0 should be 0, which should be in I because of this second property. So 0 is always there in your ideal. So this is not a must condition, like this is not not a new condition to put in. So ideal already has 0. So 0 belongs to any ideal. Okay. So because of this, now let's see if we have any example which does not satisfy this property. What is that? Can you think of any example?
Set of integers Z.
Yeah, let's take, R is your Z and what is your A? Okay, so you have exactly, to start with you can always take integers, and that is a very good example always. So you have ring to be a set of integers, then you just take A to be anything like multiples of 4 or even multiple of 2 or whatever you want. Okay, so just take any. So for example, let's take this 4 multiples of 4, which is what? R belongs to Z. Then certainly A is not equal to R because 1 is not there. These are the set of integers, and this just says these are the multiples of 4. So obviously this statement is very trivial to say this is not the case, because otherwise what is the point of introducing ideal? So 0 is always there, but So why, when this becomes true, when if you say that 1 belongs to A, if you say 1 belongs to A, then A is always R, because one, that is multiplicative identity, because 1 is there. So that means because of this property, if you 1 is there, so you just take 1 here and take any element R, then this belongs to R. So 1 into R, you can choose R any of the element of your ring. So that means you have R belongs to I, so that means all the elements of ring you have in your ideal, so this has to be the equal. Okay, so when you have been said that 1 belongs to A, then this is true, but not with 0, because 0 is always there, so additive identity will not work, right? Is that clear? So okay, second statement is false. So what is that? S1 is true and S2 is false. Very good. If you have any doubt, you can write it in chat box, or you can speak, unmute and speak. Okay. In the ring of integers, find a positive number A such that this happens. Okay. Okay. Before doing this question, I want to do this question first. So let me do that, because something is better to be known first for question number 4, which is in 5 actually. Given below are two statements S1 and S2. Okay, choose the correct option regarding these statements. So you have been said, so S1 is operation star is defined, so A star B, so this is for S1. So A star B is given to be this, so you have some operation star, and where A and B are complex numbers. Then C comma star is a group or not? That is your question. Is a group or not? So this is your question. Now let's see if we have this or not. So to check if this is a group, what should you check? You should start with the basic things.
Closure, associativity, identity.
Exactly, very good. So you should start with closure first. So I'll just change color. Okay, so closure. So A star B, which is equal to A square B. So you have some random elements A, B in your which are complex number. Then A star B is your this element. Then whatever you get root of something, that is also an element of C, right? Even if you, anyway, so inside this, whether you get negative, whether you get positive, you don't have to worry. So you have always this element in your complex number, because if it is minus of something, then you have iota, which is also a complex number, right? So closure is fine. What about associativity? A star B star C. So first take this, then you will get A square plus B square star C. Then again you apply this operation, you will get root of A square plus B square root of this square plus C square, right? And root and square will make it A square plus B square, which is C square. And if you want to see, you can always see it directly, like you can do this, and this is actually, so I'm going from the same way. So this is A star root of B square plus C square, and this will be your so if you are confused with going back, you can always do this, like, which I feel actually valid and safe. So this is, now take this side and do the same process. So A star root B square plus C square, and you will get again root A square plus B square plus C square root and square. So you will get, as you have got earlier, you got the same thing. So these are same. So associativity is fine. Okay, what about identity? Can you think of something? What can you take? Or can you take something? What do you think? Yeah,
0.
0. Okay, that is definitely an option. So a star 0, let's take that is a square plus 0 square, and that you will get root a square. So the problem with 0 is you can have minus a here, or you can also have a here. Because of that, identity is not defined, because if you take minus a into 0 to start with, you can say this is a, or even you can say this is minus a. So this is not really a good option to begin with. Like if you take minus a star 0, okay, right, yeah, I was just thinking like can so basically the problem is this multiplication is not really properly defined, because you can think of like you are having minus a or a, that is both fine, because minus a square and then root. So this multiplication is not really defined in a way. So you can say you got minus a because right. So minus a star 0, you got minus a square plus 0 square, and that is your a also, minus a, as I said. So so you start with this, but you got a, then 0 is, so basically 0 is not, so identity is not defined here. That is the problem, right? So this is not a group, not a group. Okay, let's see about S2. So what is your second thing? S2. S2 says every ideal, so this is wrong. Every ideal of the ring Z plus star is a principal ideal. So you have ring of integers, which I was saying, which will be used in your previous question. Every ideal of the ring Z plus star is a principal ideal. So that is your so this has been asked. Okay. Okay, I'm saying this is true, and I'll prove it also. So claim is, okay, I should not start with claim. Let's say this is your ideal. Let I be an ideal of Z plus star. Okay, first thing, what is a principal ideal? So okay, I should go with definition first. What is a principal ideal? Any ideal I is said to be a principal ideal if there exists A belongs to I such that I is equal to generated by A. So generated by A means the set A into R, where R belongs to R. So you can write all the elements as a multiple of some element. Okay, so that is the definition of principal ideal. So let I be an ideal. So you need to prove that any ideal you pick of a set of integers, you will always land up like it will be a multiple of some fixed element. So let's see if this is true. So let I be an ideal of Z plus star. Let A is A be the smallest positive integer. That is always possible, because whatever you have, you can always find smallest positive integer in your in your ideal, positive integer of ideal I. So let's take a is your smallest positive integer in I. Then what will happen? So my claim is I is actually generated by A. So I is your ideal, which is generated by A. So let's prove it. If not, if this is not true, then what will happen? There exists some B belongs to I such that, so this is the symbol of there exist. If you don't know, I am just writing to so this is there exist. Okay, so there exists some B in I such that B is not a multiple of A. So B is not a multiple of A. Okay, let's see if this is true or not. Also, so this is smallest. B is okay, yeah, that's fine. B is not a multiple of A. Now let's take some element. So what is GCD? So GCD of A and B. So what is GCD? GCD is equal to okay, one second, I just need to say something. Okay, let's see if it is required. I'll mention. So GCD, what is GCD of A and B? This is something A alpha plus B beta. So what is the definition of GCD? Smallest element such that there exist smallest element in the set alpha, smallest, again positive integer, smallest. So what is GCD? Smallest positive integer in the set alpha A plus beta B such that alpha and beta belongs to Z, right? That is the definition, right? So smallest positive integer which you can have with the linear combination. Okay, this is okay. So smallest positive integer in the set alpha A plus beta B, that is your set. Okay, so here if you see alpha A plus beta B, so what is this? So this element, whatever alpha and beta you have, this element, so this part is a multiple of A, so this should be in I, because I is an ideal. So I is an ideal and Z is your integer, so this is your ring, right? This is your ring. So you have some multiplication with from the ring to A, and A belongs to your ideal, so this should be an ideal. Similarly, B belongs to I, so beta into B should be in I. And with ideal, what do you have? The property that the sum of two elements is also in I. So sum of two elements which are in I will be in I too. So this will be in I. So alpha A plus beta B belongs to I. And now this is your GCD, right? So GCD of A and B is some element of this kind, right? Yes, tell me. Who raised the hand?
Sorry, by Miss.
Yeah, yes, Sai Kumar.
Yeah, it was by Miss. Clicked that.
I didn't get it, sorry.
By Miss, I have clicked that. Sorry for the interruption. You
Okay,
can continue with the class.
okay. So should I continue?
Yeah, sure.
Okay. So AB plus alpha A plus beta B belongs to I. So any element, so any element which is of this kind, so GCD is some element of this kind, so this belongs to I, right? GCD of AB belongs to I, but A and B does not belong to I. A does not divide B. Okay, that something, as I said, I should mention that. Okay, so b is not a multiple of a, and a is your smallest positive integer. So one thing I am saying, if if b belongs to I, are you convinced that minus b will be in I too? Okay, so yeah, tell me. So I'm saying if b belongs to I, or I'll say just random, not say b, if some element r belongs to I, then minus r belongs to I in integer set, in integers. So if you have I is a I, okay, let me write it in this form. If uh, if r is equal to z plus star, then if r belongs to, okay, I can write it in this form, then r belongs to I if and only if minus r belongs to I. So are you convinced with this fact? And I is your ideal, okay, where I is an ideal. Can you tell me why this is true? Anyone? Just think of this statement. I'm not saying. Yeah.
In ring Z there is minus 1 element.
Yeah. And which property will be used here?
Second one.
Yeah,
They are
exactly. Very good. So in the ideal you have two properties. The sum should be there, and if you multiply any element of ideal to any element of ring, you will be in your ideal itself. So r belongs to I, so minus 1 into r belongs to I, so you have minus r belongs to I. So what I want to correct here, I want to say, just to make it clear, that I am choosing, so because of this property, as I know b belongs to I, so minus b belongs to I, so I am choosing, if not, then there exists b will a positive integer. So I am saying a positive integer. So is that okay if I choose b to be a positive integer? Because so if not, then there exists a, without loss of generality, I could say I can choose some element which is positive, such that b is not a multiple of a. Is that okay? Because if you have minus b there, then you will always have b. So you have, if you have negative integer of that number, like if you have negative integer, then you have the positive integer of the same value. Okay, same norm basically. Okay, so because of this, so why I am saying that, because just to make the result convincing, so I said GCD of AB belongs to I. Now you know B is a positive integer and A is the smallest positive integer in your ideal, then B must be uh, greater than B, right? Because A is the smallest integer. Okay, smallest positive integer, and B is a positive integer which belongs to I. So A is definitely, sorry, B is definitely bigger than A, right? So because of this, GCD of A and B. Now you know B is not a multiple of A. So GCD of A and B, what is that? It is always less than A, always less than or equal to B. Like it could be equal or it could be less than also. So you know B is bigger than B. So this implies GCD should be less than or equal to A. But you know B is not a multiple of A. B is not a multiple of A. So because of this, it cannot be equal to A. Because for example, you have B is equal to 5 and and A is 2. Then if you see, the GCD cannot be 2, because 5 is not a multiple, because GCD of A and B always divides the elements, that is A always also divides B, right? If you say this is equal to B, then you are having a contradiction itself here. So this what should be the case? GCD of AB is exactly less than A. Also, this does not belong, sorry, this belongs to I because of this property, as we said here. So this belongs to I. GCD of AB belongs to I. And but you already said, and this is a positive integer, right? Because from the definition, right? So you are actually done. So you are saying you have some smaller integer than A, smaller positive integer than A, which is an I, which is a contradiction to your what you have picked up A as. Like A was the smallest positive integer to begin with, right? So this is not true. Is that okay? Is that okay?
Yes.
Okay, very good. So if you take, so my claim is true because I started with contrary. So I is equal to A. And what A is? A is the smallest positive integer which belongs to I. Okay. So as I said, because of this, so all the ideals, whatever ideal you will take, you will be that will be your principal ideal. It will be generated by some element. Also, one more thing, we have taken every element. When can you not find a smallest positive integer? When the set is itself 0. So if you have just 0, that is also an ideal. So if you just take 0 ideal, then it is generated by 0. So you have covered all the ideals. So all the ideals in the ring Z are principal. Okay, so S2 is true. So what is that? Only S2 is true. Okay, now I can come to this question. So what I was saying, so you are in the ring of integers. So all the ideals are generated by single element. So you have this ideal 12 plus 16. This is an ideal. So this is exactly generated by element 12, and this is generated by element 16. Okay. So this is an ideal. What is the definition of sum of ideals? Is like you just take 12 into A1 plus 16 into A2, where A1, A2 belongs to Z. This is the definition of sum of ideals. From I1 plus I2, you will just take all the linear combinations where this belongs to, yeah. So this is, so okay, I can write. This is what? This is A1. Okay, notations are very bad. So let's take this. I don't know. I can write it better, I guess, but okay. R1 belongs to I1, R2 belongs to I2, and A1 and A2 belongs to R. Okay, so you take the linear combination from I1 and I2. So this is your definition for addition, and you can check this is an ideal. Okay, these are from the lectures itself. Here, so you have been asked that this is equal. Okay, so sorry, this is an ideal. Now if you know, you have proved that any ideal of the ring of integers is principal. That means it should be generated by one element. That's why they have asked, can you find some A such that this will happen? So you need to find A. So according to our process, according to the process we did here, A should be what? A should be the smallest. A should be what? A should be the smallest positive integer. A should be the smallest positive integer. Okay, actually you can have negative also. That is also fine, because if 2 generates the set, then -2 also generate the set. Okay, but as you see in the options, these are all positive, so you can go with A should be the smallest positive integer. Okay, positive integer belongs to this A should be the smallest positive integer of the set of the ideal, or maybe of the ideal this. Okay. Actually, if you see what is that smallest element, if you see from the process itself, A should be the GCD of okay, I should not go better. Okay, so A should be the smallest positive integer of the ideal this. Okay, so A okay, I'll write it as again claim. So claim is A is equal to GCD of 12 and 16, and that is 4. Okay, as you know, GCD of 12 and 16 is 4. So I'm saying this is my claim. So to prove this, if you want to see, A is the smallest positive integer of the ideal this. So the ideal this is what, as I wrote earlier, this is equal to 12 into A1 plus 16 into A2, such that A1 and A2 belongs to Z, right? So what is that? What is this? This is again a combination of 12 and 16. So if you want to see smallest number of smallest positive integer, so this is exactly the definition of GCD, right? Smallest positive integer in the set this, which will be equal to what? Smallest of this set, right? And which is exactly your what is that? Smallest of this is GCD, right? So as I said, claim is proved. So that is 4. So 4 is true. Is that okay? Is that okay?
Yes.
Okay. Okay, let's move to the last question for today. How many number of reducible polynomials of the form this are there in ZP where P is a prime? Okay, so the question is asked how many number of reducible polynomials of the form this? So you have x square plus ax plus b. Okay, so reducible polynomials, what does that mean? So from the definition of reducible, okay, these are in ZP. So okay, are there in ZP? Okay, do you know what is ZP? ZP is exactly which you have used earlier, no doubt. So this is the ring of, this is 0, so bar I should put, no doubt. Okay, so this is your set. So this is your ring, no doubt. If you want to check, you can always check all the properties. So this is your ring. Now so reducible polynomials, what does that mean? Reducible means you can write this as x plus m and x plus n. The product of two linear polynomials. Why I wrote linear polynomials? Because if you have something like, let's say you have alpha and you have whatever, I don't know, a1 x square plus a2 x plus a3, let's say this, you have something. When you if you can write it like this, then alpha is what? Alpha is an element of this, alpha is an element of ZP. So this is invertible, because if you take alpha, so in ZP, inverse exists, right? If you take so inverse is always there. For example, if you have alpha to be q, then you can always take what? You can always take p minus q. So q is bar, like, okay, q is a very bad integer to take. So alpha is an element in zp, right? So this is what, how shall I write? So why this is invertible? Because if you take alpha and that is in zp, so this is less than p minus 1, and then take multiply, what am I saying? Okay, you can always find this. Okay, in zp, I guess you have proved this. So this is a group. So with multiplication, this is a group. If this is prime, then it is always a, okay, yeah, you have, there you don't have 0, right? So when you take, this is star. Okay, I'll write one thing here. So I'll put it as an exercise, because you must have done that. Exercise zp star. If you have any doubt with the definition, let me know. This is multiplication, okay? Multiplication under p. Like when you multiply, for example, you have p equals to 5 and you take 2 into 3, you will get 6, and that is equal to 1 in zp, okay? And you are not considering 0. This is star means, okay, I can write it, zp minus 0. This is a group. Okay, just solve this exercise. If p is prime, if p is prime, so this is only true and this is prime, okay? Yeah, so if p is prime, then this is a group, okay? Just check it. So because of this, what do you have? You have alpha to be invertible, and when you are looking for reducible polynomials, so we are in the set of polynomials. So okay, I should write it, zpx, you have this, you have this as is your ring, okay? And the usual multiplication and addition is the ring to deal with, okay? This is the ring which we are dealing here, and now we are searching for reducible polynomials of this form, okay? So I am saying, if the condition, like if the polynomial can be written in this form, then you are not actually, so this is not actually reducible, because alpha is invertible always. So to have the reducible polynomials, the condition should be this. Reducible polynomial implies this equation should be true, okay? So you can write it as the product of linear factors, okay? Not quadratic, linear factors. You cannot, definitely you cannot go to cubic or something, because the polynomial itself is quadratic, okay? So that was the first point. And then now, so we are saying reducible means, here reducible, quadratic, reducible, x square plus ax plus p is reducible if and only if x square plus ax plus p can be written as x plus m into x plus n for some m and n belongs to zp. You are in zp, that is also important, okay? Now if you want to count, so the question was to count how many number of reducible polynomials are there of such kind. So if you can count this thing, then you can count this value, right? So let's count how many x plus m and x plus n you can have in zp, okay? In zp, how many such kind of thing you can have? So first thing, let's say these are distinct, okay? Let's say for counting, let's say these are distinct. Then what all the possibilities you have? You take, here you have p possibilities, and here you have p minus 1 possibilities. You are just taking the count, you have some m and n. So let's say for distinct, so first m and n, so I can write it here. So first m and n are distinct. Okay, with this thing you have, if m and n are distinct, then what possibilities you can have? Here you have p possibilities, here you have p minus 1 possibilities, and you are just taking. So if you, let's say here you have 1, then you have you can have 0, 1, 2, 3, 4, and we as I said, if m is 2, then you have n to be 0, 1, 3, 4, 2, and so on, p minus 1. Just ignore 2. So because we said these are distinct. Okay, so these are all the options, p into p minus 1. Now if you have 2 here, so this is also other way around, because why I wrote by 2, because x plus n into x plus m is also same. This is same as x plus n into x plus m. So if you take for example here 2 and here you have 5, then x plus 5 into x plus 2 is also same, right? So everything is counting twice if we just take p into p minus 1. So we need to do by 2. Second, if m and n are same. Okay, if these are same, then what will happen? You have something, let's say m, and again I can write, as these are same, just write it m. Then what are all the possibilities? You just have p possibilities. Just take p. Like p means you have some any element of zp, then the same element is here. Okay, so total count is number of reducible elements, reducible polynomials required. I'll just write required reducible polynomials is equal to p into p minus 1 by 2 plus p. And if you calculate, this is exactly equal to p square by okay, p square plus p by 2, that is equal to p plus 1 by 2. So the answer is this, fourth one. Okay, so I am done with my questions. If you have any doubt, just let me know.